Hello, my name is Sohail Sheikh and my project is inspecting building structures using autonomous drones. My advisor is Dr. Arian Placo. Large and complex building structures such as bridges, dams, skyscrapers, and even residential buildings require inspections to detect any structural damage because of age or naturally occurring events that lead to structural weakening. Arranging such an inspection is time-consuming, dangerous, costly, and requires special skills and equipment, especially if the inspection involves tall and complex structures such as dams, bridges, and skyscrapers. An intelligent semi-autonomous drone or a swarm of drones equipped with a high-fidelity camera and LiDAR sensor is one of the solutions to solve this problem. My project has multiple phases. The first step is to conduct initial research to understand the current state of drone research and development, related applications, tools, and the platforms that are being developed and used by the community. Next, develop a platform for experiments and prototyping. Then, conduct experiments to learn the behavior of various components involved. After getting a better understanding, develop prototypes and implement various parts to accomplish collectively the overall goal of inspecting a structure, followed by documenting the findings, challenges, results, and ideas which are available in my project report. The intent was to start small and expand gradually as the learning progressed. Last, determine the direction of the future research. Initial research. I started out by researching the internet about ROS, Gazebo, and reading research papers on this topic. The software stack includes Ubuntu Linux, ROS, Gazebo Simulator, ArduPilot, Python, C++, OpenCV, Catkin, drone control libraries, and other packages. Just to give a quick introduction to various software in the stack, Ubuntu Linux is a popular Linux distribution and it is required by ROS to work. It provides an excellent environment for software development. ROS and Robot Operating System is an open source middleware platform developed for robotics on top of Ubuntu and provides an extensive set of capabilities for robot development right out of the box. Gazebo is a 3D physics-based open source simulation environment funded by DARPA and maintained by Open Robotics. After selecting ROS and Gazebo, the next question was how to simulate the drone. It turned out that there is a very large and active community of drone developers and they have developed ArduPilot software for real drones and also include plugins for Gazebo simulation. What is a drone? A drone is a common but very broad term and covers different variations of unmanned aerial vehicles, UAVs. The focus of this project is the quadcopter shown on the right, which is the most popular drone type for hobbyists and commercial use. Drone control. Upon research, the ArduPilot project was found on GitHub, which covers 5 different types of vehicles: pilot, copter, rover, sub, and blimp. As we can see, 3 out of 5 are flying objects. In addition to ROS, Gazebo, and ArduCopter, I needed a mechanism to control the drone. 2 options were found: ground control station and scripting. For GCS, there are 2 popular options: Cube Ground Control and Mission Planner. These screenshots are captured for the 2 ground control stations I have tried. Cube Ground Control is a very robust GCS and works well with ArduCopter on Linux. Mission Planner has extensive support for ArduCopter, but only supports Windows natively. I was unable to make it work on Ubuntu 18. Scripting. For scripting, there are several options ranked by the precise level of control they offer, as well as level of difficulty. Mavlink is a low-level, very lightweight messaging protocol for communication, typically used with programs written in C and C++. PyMavlink is a Python wrapper over Mavlink protocol, provides low-level functionality similar to Mavlink but in Python. MapProxy is a fully functional, minimalist, portable, and extendable command line GCS using Mavlink protocol. DroneKit is a high-level library but only supports Python 2. It is no longer in active development since 2015 and does not support the newer ArduCopter versions. Intelligent Quads GNC is another higher-level Python library that worked for the project but offers limited functionality and lacks precise control of the drone. Implementation. The implementation is divided into two phases. Number one, installation and configuration of all the required components that must work together. These components are Ubuntu, ROS, Gazebo, Ardocopter, Python, DroneKit, or GNC, and not cause compatibility issues. And this turned out to be the most time consuming phase of the project for several reasons. All these open source software are developed by different teams with different and sometimes competing goals and development timelines, which causes incompatibilities. Number two, experimenting with the drone named Ardocopter Iris, learning its behavior after sending various commands using map proxy CLI or the high level libraries such as GNC, and developing a control script based on the original goal using Python. In the end, a waypoint based mission plan was created using GNC and Python. To develop a waypoint based mission plan to inspect the cylinder, I needed to generate waypoints around the cylinder. I used the equation for a circle for this purpose. To simplify the task, I used only one drone for the proof of concept. Quadcopter design. A basic quadcopter such as Iris used in the simulation consists of a basic frame, shown on the left, and control electronics and sensors on the right. The selection of various sensors is dependent on the mission, but weight and power consumption are also considered for the final configuration. LiDAR. LiDAR sensor was planned to be used to detect the direction and to keep a constant distance from the target object. However, it suffered from drift as well as reading inconsistency. Therefore, in the final control program, it was not used for calculations. It was kept turned on and not visible in the pictures, however. For image detection, the project used a darknet YOLO library. It has some practical issues, one being a computing resource hog that crashes the laptop every time it was used, and inconsistent image detection. For example, it was detecting a person only 50% of the time and rest of the time something else. Software installation. This is the software stack used in the project. Please note the specific versions of these software packages since they caused a lot of time spent trying different versions to work with each other nicely. Challenges, or rather learning opportunities. During this project, I learned new ideas, concepts, and a few valuable lessons. There is a steep learning curve for ROS and Gazebo given the time constraint. Implementation issues with Ardocopter. Sole reliance on a popular but non-working library for controlling the drones. Earlier versions may have limited features, but they are likely compatible and reliable. Had to spend more than a month just to figure out which versions of software do not cause incompatibility problems. In addition to incompatibility problems described earlier, there are other challenges. Darknet YOLO image recognition technically worked, but crashed the laptop every time it ran, so I had to abandon its use until I find a better solution. It barely worked on my high-performance workstation. LiDAR has two issues. One, its direction readings have drifted over time. Two, the readings were inconsistent for the same stationary object. I had to stop using LiDAR for finding the target's direction. IQGNC library was the last resort after finding that DroneKit library is not going to work for Ardocopter. It suffered from inaccuracies too, but worked in general to accomplish the task. Results. After failing to use YOLO image recognition or LiDAR target heading detection successfully, I decided to use waypoint-based inspection script written in Python. The challenge was to use calculated waypoints and program the drone script with these waypoints. Although more waypoints can be programmed, I decided to use only 12 waypoints and a 1 meter height increment per cycle, and there are 10 cycles equal to 120 waypoints in total. The entire run can take a continuous video or take pictures at each waypoint. Several videos and pictures are captured of the runs. It was an excellent learning project, and I learned more in the past 3 months than I learned in the previous 3 years about UAVs. The challenging part is to figure out which component causes what kind of incompatibility, realizing that all these open source components are developed by different teams with their own goals and schedules, consequently causing incompatibility issues. ROS provides several tools to help the developers, such as RQT, which is used for monitoring topics such as an onboard camera shown here. In these pictures, I'm showing a swarm of drones inspecting a building and a cylinder. Future research. Some of the ideas that I originally had for this project can be used for future research, such as training a swarm of drones to work autonomously completing their tasks. Use of AI in training these drones so they can detect structural problems. Research and develop algorithms and techniques on how drones can divide up their tasks among themselves on their own. Develop efficiencies so drones are lighter and cheaper. References. These are some of the references I used during my early research. Backup material. ROS nodes communicate with each other using messages. Instead of point-to-point communication, ROS uses publish and subscribe communication pattern using topics, which is scalable compared to P2P. ROS provide tools for a visual representation of nodes, publishers, subscribers, and topics shown below as an example. Drones and reference frame. A reference frame is a key concept in drone development. Setting and getting the right reference frame is required to implement waypoint-based mission plans. The figure shows coordinates that are used in the reference frame. Thank you very much for listening to my presentation.